In many applications, diodes are used to clamp voltages in circuits. This is because diodes have the property to limit voltages and signals if placed right. For hard clipping or limiting of voltage, the diodes are placed in parallel to the signal source. This is often also done with a series resistance to make sure that the diode does not get damaged. Every diode also has the property to have a certain forward voltage. This is the voltage that's needed for the diode to start conducting. This can also be seen as a threshold that triggers a switch. A general-purpose silicon diode has a forward voltage of about 650 millivolts. To understand the working principle, I will draw the input and output signal of this hard clipper configuration. At first, the signal is under the threshold level or forward voltage of the diode. The diode behaves as an open circuit, so the output will be equal to the input. Then the input signal crosses the threshold value. The diode starts conducting and the signal is held at the threshold voltage. This is what's called clipping. A part of the input waveform is clipped off by the diode. Now this circuit only clips positive voltages, if they reach the forward voltage. This will lead to asymmetrical clipping, because the negative going signals will stay unharmed. To make sure both positive and negative signals are symmetrically clipped, another diode can be added in parallel but facing the other way. Now with an arbitrary input signal, the output signal will be clipped at two threshold values. What if 650 millivolts of protection is too much or too little? If it's too much, you can replace the diodes with Schottky diodes. This can lower the threshold voltage to as low as 200 millivolts. If you want more, you can put the diodes in series to make the total forward voltage higher. If you need something more precise, you can use Zener diodes that clip one way with a standard silicon forward voltage and the other way with its rated Zener voltage. So if you have to protect a sensitive pin of, for example, the ADC of a microcontroller, all you have to do is add a Zener diode in front and a bit of series resistance so the diode doesn't burn out when it conducts. In this case, this might be a 5-volt system, so a Zener diode of 5.1 volts might suffice. This is very dependent on the maximum voltage ratings for the ADC input, which can be found in the datasheet. Another way is to use two Schottky diodes, of which one points towards the positive supply rail. Now the input signal is clamped between negative 200 millivolts and positive 5.2 volts, because the Schottky forward voltage is added to the supply voltage. But maybe you're more interested in the musical ways to use hard clipping. For example, hard clipping is used extensively in effects pedals. In this case, we will analyze the distortion plus by MXR. At the input of the op-amp is a basic biasing network that makes sure that the AC guitar signals get a DC offset between 0 and 9 volts. Next is an op-amp in the non-inverting amplifier topology. With potentiometer RV1, the gain can be increased to a maximum of 213 times. This amplified signal is then presented at the output, pin 6. Because we want an AC signal without DC offset due to the bias at the output of the effects pedal, capacitor C1 is added. After this, the amplified AC signal is passed to a clipping section with two diodes. This section will symmetrically clip the signal and add a distorted effect to the sound of the guitar. So if you simplify the schematic to its building blocks, it is visible how the last two blocks work together in clipping the signal. The more gain is added to the input signal, the more the clipping stage distorts the signal because the forward voltage is constant. This is called driving the signal into clipping. Thanks for watching this video, like and subscribe if this was useful, and see you in the next one. Bye!